Okay, I want you to picture the ultimate manufacturing nightmare.
Oh, I think I know where you're going with this.
You've been standing in front of a high-precision grinder for, say, 6 hours. Your back hurts, you're sweating, but you are focused because this mold you're making, it needs to be perfect.
We're talking a true mirror finish. Something you can literally see your reflection in without a single flaw.
Not even a little distortion. The kind of finish where, a fingerprint looks like a crater.
Exactly.
So the machine stops humming, you pull the piece out, you hold it up to the inspection light, you're expecting just glory. And there it is.
The scratch.
A single, deep, devastating scratch running right across the surface.
That is just a heart-stopping moment. It's not just a scratch, it's a failed day.
It's a total disaster. You've wasted the material, you've burned all those hours, and you've effectively just lit a pile of money on fire. Now, my first instinct, and I'm guessing the instinct of most people listening, would be to blame my hand, or maybe the grinder itself.
Right. The machine malfunctioned or I slipped. That's the natural reaction.
Yeah.
But if you're chasing that sub-micron mirror finish, I would bet good money it wasn't your hand, and it probably wasn't the steel of the machine that failed you.
So what was it?
The culprit is almost always the auxiliary support system.
Which is a very fancy way of saying the coolant.
It is.
See, this is where I got stuck when I was reading the research for this deep dive. I've always thought of coolant as just machine juice.
Yeah. Sure. Soapy water.
It's soapy water you pour in a tank to keep things from overheating. It feels like a commodity. You buy it, you use it, you dump it. But you're telling me this liquid is actually the main character in this story?
In mirror grinding. Absolutely. If you treat coolant like a simple consumable like paper towels or shop rags, you will never, ever achieve a perfect finish.
So what's the alternative?
You have to completely reframe your thinking. You need to stop seeing it as just water and start viewing it as a critical component of the machine's geometry.
Liquid geometry. I saw that phrase in the notes, and I have to be honest, it sounds like a contradiction. Geometry is solid, it's rigid. How can a liquid be structural?
Well, think of it this way. The coolant fills that tiny gap between the tool and the work.
Okay.
It dictates the temperature, which, as we'll see, dictates the actual size of the metal. It dictates the friction, which determines the surface quality. If that liquid layer fails, the physical geometry of the machine, it fails too.
So the fluid is effectively a moving liquid part of the machine's own structure.
That's it, exactly.
Okay, that definitely sets the stakes a lot higher than just soapy water. So today, we're going to tear apart this idea of liquid geometry. We're going to look at the 3 ways this system tries to kill your mirror finish.
It's a battle on 3 fronts.
The microscopic violence of debris, the invisible enemy of heat, and the chemistry you need to actually make it all work. Let's start with the violence. We open with that nightmare scratch, but in the research, it described the damage in a really specific way. It's not just a line, is it?
No, not at all. If you put that scratch under a microscope, or even just look at it under a really powerful inspection light, it tells a story. We call them comet tails.
Comet tails. It sounds almost beautiful, but I'm guessing it's not.
It is definitely not beautiful to a machinist, but the name is accurate. Imagine a comet in the sky. You have that bright, dense head, and then a long, fading tail trailing behind it.
Right.
That is exactly what the damage looks like on the metal. You get a deep gouge at the start, that's the head, where the impact happened. And then, as the particle rolled or broke apart, the scratch gets shallower and fades out. That creates the tail.
So walk me through the physics of that moment. What is actually happening inside the machine to create a shape like that?
It all comes down to the gap. In mirror grinding, the distance between the spinning grinding wheel and your metal workpiece it's incredibly small.
We're shaving off atoms, almost.
We're trying to shave off material at a sub-micron level. Now imagine your coolant is dirty.
And dirty means what? Like mud?
No, not mud. Dirty, in this context, just means it contains microscopic debris.
Yeah.
Detached abrasive grains that fell off the wheel. Tiny metal chips from the part you're cutting.
Or even just dust from the shop air.
Or dust from the air.
Yeah.
Exactly. So these little landmines are just floating in the liquid.
Okay.
The coolant floods the grinding zone. The wheel is spinning at thousands of RPM. It catches one of these particles, and it drags it across the surface of the workpiece.
And that's the impact.
That initial impact, where the wheel physically forces the particle into the metal that digs the deep head of the comet.
And because the wheel is moving, it drags it along.
It drags it. But the particle doesn't just stay there. It might roll, it might bounce, or it might just shatter under the pressure. And as it does that, the pressure releases slightly, and the scratch fades away. That's your tail.
Wow.
If you look at it under 200x magnification, you can actually see the pluck-out point where the metal was physically ripped out.
It sounds incredibly violent.
It is violent. It's
Yeah.
microscopic trauma.
I want to pause on the scale here because microscopic is a word we throw around a lot. The target surface roughness for a mirror finish is an ACK of 0.2 microns.
0.2 microns, that is, that's smoother than glass.
And the debris we're talking about, the stuff that ruins the job, might be 10 or 20 microns in size.
Right.
To my naked eye, a 20-micron speck is invisible. It's nothing. But in the context of this machine, how big is that, really?
Okay, let's use an analogy. Imagine your target surface finish, that perfect 0.2 micron smoothness, is the surface of a calm, flat pond.
Okay, I'm with you.
A 20-micron particle hitting that surface isn't like skipping a stone. It's like driving a pickup truck into that pond at 60 miles an hour.
Whoa. Okay, that puts it in perspective.
It's absolutely catastrophic. Relative to the tolerance you're trying to hold, that tiny speck of dust is a boulder. If that boulder gets between the wheel and the work, it's game over.
And the research mentioned this debris doesn't just scratch things once. There was a term, secondary cutting, which sounds like the sequel to a horror movie.
It's the sequel nobody wants to see. Secondary cutting is what happens when you don't filter that swarf the chips and sludge out of the system.
Right.
The grinding wheel comes around for another pass. It picks up the trash from the previous pass, and it presses it right back into the metal.
So you're remachining the surface using your own garbage as the tool.
Precisely. You finish the pass, the surface should be perfect, but because the coolant was carrying those old chips, you just drag them across the finish. You ruin the gloss instantly.
Yeah.
And it's entirely self-inflicted.
So we've got the pickup truck driving into the pond. That's the physical debris. But let's say you solve that. You have the cleanest filter in the world. You're feeling good. But then the afternoon rolls around.
Yes. The perfect morning, terrible afternoon syndrome.
Is this a real thing?
Oh, every machinist I know has lived this. You come in at 8 a.m., the machine is cold, you set it up, run the first part, it's beautiful, measurements are perfect.
Great start to the day.
You run production all morning, you go to lunch, you come back, run the exact same program, same settings, same everything. The part is scrap. It's oversized, or the finish has these weird burn marks. And you spend the rest of the day chasing the dial, trying to figure out why the machine moved.
But the machine didn't move. The liquid geometry moved.
You are catching on. This is the thermal expansion problem. We have to remember that metal is extremely sensitive to heat, and there's a brutal math to it.
The source gave a specific formula for steel. I wrote this down because I wanted to test you. If I have a steel part, how much does it grow when it gets hot?
The rule of thumb is 1.2 microns per 100 millimeters of length for every single degree Celsius rise in temperature.
1.2 microns per degree. Again, that sounds like such a nothing number. Oh, we grow a micron, who cares?
And if you're building a bridge, nobody cares. But if you're mirror grinding with a tolerance of, say, plus or minus 1 micron.
That's your whole margin for error.
The whole thing. Gone.
So let's play that out. Let's say the coolant tank just sits there and warms up by, 5 degrees Celsius over a shift. That doesn't seem like much.
5 degrees is a total disaster. If you have a 100 millimeter part and it heats up by 5 degrees, that steel has expanded by 6 microns. Your tolerance is 1 micron. You are now 6 times out of spec.
So you grind it until the machine says it's the right size?
You grind it while it's hot and swollen. The machine thinks it's perfect. Then you take it off, put it in the inspection room. It cools down back to room temperature.
And it shrinks.
It shrinks. And now your part is undersized. It's trash.
And this heat isn't just coming from the room air, right? It's a feedback loop inside the machine itself.
That's the insidious part. Grinding is friction. Friction creates heat. The coolant's job is to carry that heat away. But if the coolant itself is already warm, it can't absorb any more energy.
So the wheel gets hot.
The wheel gets hot. When the wheel gets hot, the lubrication film breaks down. And when the lubrication fails,
You get more friction?
the wheel starts to glaze. The pores clog up. Instead of cutting the metal cleanly, it just starts rubbing against it. Rubbing creates more friction, which creates more heat.
It's a snowball effect.
It is a runaway thermal event. And that excessive heat creates burn marks on the surface. So you end up with a part that's the wrong size and has a ruined finish.
So you can't just, blow a fan on it.
Now, this is why high-end mirror grinders have independent refrigeration units, chillers. You have to actively refrigerate the coolant to keep it at a precise, constant temperature.
You stop the thermal drift.
If you stop the fluid from changing temperature, You stop the part from changing size. You stabilize the liquid geometry.
Okay, so we've identified the two main enemies, the debris, the boulders, and the heat, the expansion. Now we need to talk about how to fight them. The defense in depth.
I love that term. It implies that a single line of defense just isn't enough.
Well, that's the question I had. I mean, every grinder comes with some kind of filter. Why isn't that enough? Why do we need this complex, multi-stage system?
Because a standard filter is like trying to catch sand with a tennis racket.
Okay, that's a very vivid image.
Most standard filters are designed for chips, visible chunks of metal. They let the fines, that dangerous 10-micron silt, pass right on through.
And for mirror grinding, that silt is deadly.
It's the killer. You need a system that gets progressively tighter.
So walk us through the stages. Stage 1 is the magnetic separator.
Right. This is the brute force stage. Most grinding involves iron or steel. Magnets are great because they pull out the bulk waste, the heavy filings, the big chips.
Is this about the surface finish, or is it more about just machine health?
It's mostly machine health. If you sent all that heavy sludge directly to a fine paper filter, you'd clog it in 5 minutes. The magnets just protect the pumps and extend the life of the finer filters downstream.
Okay, so the magnets grab the big chunks. What's stage 2?
Stage 2 is usually a barrier filter, like a copper mesh or a paper band. This catches the non-magnetic grit and the medium-sized particles. In a normal machine shop, you might stop here.
But we're not running a normal machine shop. We want a mirror.
Exactly. So we need stage 3, the polishing filter. And for this, you have to filter down to 5 microns.
5 microns. Why is that specific number the magic threshold?
It goes back to the wheel itself. A grinding wheel isn't a solid rock. It's porous. It has these tiny little holes that hold coolant and carry chips away.
It's like a sponge.
It's a sponge. And if you have silt in your coolant that's larger than, say, 5 or 10 microns, it gets wedged into those pores.
It plugs up the sponge.
Exactly. And a plugged wheel rubs instead of cuts. That's what causes the burning we talk about. To keep the wheel open and free cutting, the coolant has to be cleaner than the pores of the wheel.
There was one other thing mentioned in the ecosystem section that really surprised me. Pollen.
Oh, yeah.
The source material said even opening a window can ruin a job.
It sounds paranoid, but it's true. I've seen shops where they had perfect filtration, but the coolant tank lid was left open. Springtime comes, pollen floats in through the loading bay door, lands in the tank.
And suddenly the surface finish just dies.
Yeah, it drops. Because pollen is debris. Shop dust is debris. You have to seal the system. If you're filtering to 5 microns but leaving the lid off, you're just wasting your time. It's an entire ecosystem. You have to protect the chemistry.
Speaking of chemistry, let's get to the final piece of this puzzle. The recipe. We have clean coolant. We have cool coolant. But what is the coolant actually made of?
This is the eternal struggle.
Huh?
Water versus oil.
Why is it a struggle? Can't we just use the best one?
Well, the problem is they have opposite superpowers. Water is the best coolant in the universe. It absorbs heat incredibly well, but it's a terrible lubricant.
It doesn't make things slippery.
Not at all. And oil. Oil is the ultimate lubricant. It gives you that beautiful silky cutting action. But it holds on to heat. It doesn't cool the part down very efficiently.
So for mirror grinding, what do? You can't have both.
You mix them. But the ratio is critical. In standard grinding, you might use 3% or 4% mixed into water. But for mirror finishing, the sources recommend pushing that way up to 8% or even 10%.
That seems really rich. Why so much oil?
You need that lubricity to protect the wheel. If the mix is too lean, mostly water, the abrasive grains on the wheel wear out too fast because there's too much friction. You need that thick, oily film to cushion the cut and get that glossy shine.
But there's a catch, isn't there? You can have the perfect mix, but if you can't get it to the actual cutting zone, it's useless. And this brings us to the air barrier.
This is a physics problem that just blows people's minds.
Describe what's happening. The wheel is spinning, and it creates some kind of shield.
Think about a car tire spinning on a wet highway. You know how it sprays water. But it also drags air along with it. A grinding wheel spinning at 6,000 RPM acts like a powerful centrifugal fan. It creates a high-pressure layer of air that just hugs the surface of the wheel.
So it's like a force field of air.
It is exactly like a force field. And if you just pour coolant out of a nozzle like a garden hose, it hits that air layer and it bounces off. It never actually touches the metal where the cut is happening.
And that cutting zone is the hottest place in the entire machine.
It can reach 1,000 degrees Celsius instantly. So you have this inferno at the contact point, and your coolant is just hydroplaning over the top of the air barrier, doing absolutely nothing.
So how do you punch through the force field?
Brute force, pressure. The research specifies you need high-pressure jets, specifically 3 to 5 megapascals.
For those of us who don't think in pascals, how much pressure is that?
It's intense. It's like a pressure washer condensed down into a needle. These jets are designed to pierce right through that air boundary layer and inject the fluid directly into the contact zone.
So it's not just getting it wet, it's a literal injection.
It's a tactical strike.
Yeah.
And that pressure does double duty. Not only does it cool the cut, but it also blasts the chips away immediately. Remember those Comet tails?
The pickup trucks.
If you blast the chips away the millisecond they are cut, they can't get trapped under the wheel. You stop the Comet tails before they even have a chance to start.
So when you look at all of this together, it is kind of overwhelming. You need the magnets, the 5-micron paper, the chiller, the 10% oil mix, and the high-pressure jets. It feels like if you miss one piece, the whole house of cards falls down.
That is the reality of high-precision manufacturing. It's a chain. If you have the pressure but the coolant is dirty, you're just sandblasting your part with debris.
Right.
If you have clean coolant but no chiller, the part grows and you miss your tolerance.
Right.
If you have everything else but the concentration is too low, the wheel wears out and you lose the finish.
It really redefines what we think of as the machine, doesn't it?
It does. We spend millions on the grinder, the granite base, the spindles, the controllers. But this deep dive really proves that the environment you create around the cut is just as important as the cut itself.
It all goes back to that liquid geometry concept you started with. The fluid is actually doing the work.
Absolutely. The machine provides the motion, but the coolant creates the quality.
So, to wrap this up, if someone is listening to this and they're struggling with their surface finish, maybe they're seeing those scratches or fighting that thermal drift, what's the one takeaway?
Stop calling coolant a consumable.
Stop treating it like it's toilet paper.
Right. It's not something you just use up and throw away. It is a dynamic, living component of your manufacturing process. If that fluid is responsible for the geometry of your part, the finish of your product, and the lifespan of your very extensive wheel, at what point do we admit that it is actually a part of the machine itself?
That is a great question. If it determines the geometry, it is the machine. I think that's going to stick with me next time I see a CNC machine running.
Just don't dip your hand in it.
Advice to live by. Thanks for listening to this deep dive into the invisible world of mirror grinding. We'll catch you on the next one.
Stay curious.